Hello everyone. In this video, we're going to study order statistics examples. A brief overview of the video goes like this. We're going to look at two important theorems for order statistics. Then we'll take a look at some examples using these theorems. The first one will be an example finding a joint PDF using Theorem 1. And in the next two examples, we'll take a look at finding, PDFs for a particular order, or we could think of them as marginal PDFs using theorems 2. So for the first one, suppose x1, x2, and so on up to xn are independent, continuous, random variables, all having the same density f of x. Then the order statistics have a joint density. So this is a function of x1 through xn given by n factorial times f of x1 times f of x2 and so on. And this is where we get the order statistics. In the second theorem for order statistics, we identify a density of a particular order. So you might want to find the PDF of sort of the smallest variable out of all of them, something like that. So the theorem tells us if x1 through xn are independent, continuous random variables that each have the same density, then the density of the jth order statistic is given by this combinatorial term, n over j minus 1, 1, n minus j, which looks like this fraction over here, times fx xj, times, now this is the CDF of x evaluated at xj to the j minus 1 power, times 1 minus the CDF to the power n minus j. So it looks a little confusing here perhaps, but I think you'll see in an example or two this should look much clearer. Alright, so first example, and this is going to illustrate Theorem 1. Suppose we have x1, x2, and x3. They're independent, continuous random variables, each uniformly distributed in the interval 0, 10. So let's think of these as arrival times of 3 people at a bus stop. Let's say between times 8:50 and 9 o'clock. Let's let y denote the middle of the 3 values, sometimes called the median. Y is always the second smallest out of x1, x2, and x3. So we use order statistics notation. We could say y is equal to x2. Suppose we want to find the joint density of these order statistics. That's part A, and then part B. Find the particular density of y by integrating x1 and x3 out. All right, so first, each random variable is uniform between 0 and 10. So we know that our PDF for each random variable is f of x is 1 over 10, right? Remember, it's 1 over the length of the interval. So the theorem tells us that the joint PDF is equal to 3 factorial, which we know is 6, and f of x1 is equal to 1/10, f of x2 a 10th, x3 a 10th. So we get 6 over 1,000 for x1 less than x2 and so on. If I want think of this as the marginal PDF of x2, then we could put together this integral. Okay, we could think in terms of Let's go to the inner integral first. Okay, so I want to integrate with respect to x1. I know, excuse me, x1 is between 0 and 2. So we integrate between 0 and 2. 6 over 1,000. That was our joint PDF, dx1. And we know x2 is going to be, well, we know x3 is going to be between x2 and 10. So those are our limits here. And then we integrate whatever the result was from x1. So when we work this out, we get 6 over 1,000 times x2 times 10 minus x2, where x2 is between 0 and 10. In example 2, we'll illustrate theorem 2, which is all about finding the density of a particular order. So suppose we have 3 people. Let's call them Alfredo, Barbara, and Kathy. They throw darts at a dartboard of radius 9 inches. Let's let x1, x2, and x3 denote the distance of each player from the center of the board. Okay, so I want to think in terms of the distance as just a one-dimensional line segment. So this x1, the first order statistic, will be the minimum distance from the center to any of these darts. x3 would be the farthest dart, and x2 is the distance in the middle of the 3 darts with respect to the origin. And our goal is to find the density of x2. Okay, this would be the middle part. All right, so since each x is really a random variable over the interval from 0 to 9, uniformly distributed, we know that f of x is 1 over the length of the interval. So we'll call it, 1/9. And the CDF, which we would get from integrating this from 0 to x, so we use capital F is equal to x over 9. And if I think about this theorem, right, which I posted right here, okay, then we want to apply the theorem, and we keep in mind that we have 3 random variables, so n is 3, and the order that we want, the f of x2, so j is equal to 2. So this term here is really 3. We could say choose, but I have this combinatorial term 3, 1, 1, 1. So this would be 3 factorial over 1 factorial, 1 factorial. But that's going to give us 6. All right, so that takes care of this term. Then I have f of x2, but we know that f of any of these x's is 1/9. So this term here, this second term, is 1/9. The cumulative distribution, okay, would be capital Fx of xj, so x2. Remember, to the power j minus 1, since j is equal to 2, j minus 1 is 1. So this term here, this becomes x2 over 9. And then I have 1 minus the CDF evaluated at xj, or x2 in this case. And remember, this is to the power. Now this is going to be 3 minus 2, so to the first power. Okay, so by the theorem, you could see what we get. We could maybe simplify this a little bit more, but basically we get 6 over 1/9 times x2 over 9 times 1 minus x2 over 9. And so there we have it. we have the PDF of the particular order. So if I wanted to find a probability related to x2, we could simply set up the integral and use this as our PDF. In our last example, we're going to take a look at another application of Theorem 2. Suppose we have 5 people there, and they stand along a street waiting for a bus to arrive. The street is 9 yards away from a building. Now the distance in yards from each person from the street to the building has a PDF of f of x is equal to the square root of x over 18 for x between 0 and 9. All right, we assume these distances are independent, so we want to find the density of x5, the greatest of the 5 distances from the street. All right, well, x5 in this case would be the maximum. And so there are 5 ways to pick the person, and the other 4 must have a smaller distance. Okay, so we want to find the CDF of x5. Okay, so in terms of probability notation, the probability that xi is less than or equal to x5. So think of the integral here from 0 to x5, and we're integrating our PDF. I'll change the variables so I don't have too many x variables. So this becomes the square root of t over 18 dt. Okay, so treating this as t to the 1/2, you could sort of take a 1 over 18 out. So when I integrate t to the 1/2, right, we get t to the 3/2, well, divided by 3/2, but that's like multiplying by 2/3. So what I get here is x to the 3/2, well, x5 to the 3/2 over 27. Okay. So now we can use our theorem, Theorem 2. So I get my combinatorial term. Well, the n we know is 5, so I get 5 factorial over j is 5, so that's going to be 4 factorial, and minus j, you can see I left that term out, that's going to be a 5 minus 5, so that term just drops out. I have fx of x5, so that's going to be the square root of x5 over 18. And then my CDF over here, so this would be x to the 5th to the 3/2 divided by 27. Remember, j is equal to 5. Both n and j are equal to 5 here. So this becomes to the 4th power, this term. And this term just drops out because n is 5, j is 5. So this just becomes a 0. So it just drops out. And we get over here, so you could see 5 factorial over 4 factorial. It just simplifies to 5. Square root of x5 over 18 times x5 to the 3/2 over 27 raised to the 4th power. So this is a good introduction to order statistics. You can find these functions. You can do, as follow-ups, calculate probabilities with these functions. And these problems are also a good source of simulation problems that you may look at as you're learning this material. So this concludes our video on order statistics.